At this point, it is assumed that you have studied and understand the principles of amplitude modulation, as covered in You Can Do's AM radio video. As you recall, with amplitude modulation, the strength of the RF carrier wave is varied at the frequency of the information being transmitted. The louder the tone, the larger this variation in amplitude becomes. You also learn that the RF carrier frequency remained constant even though the amplitude of the signal changed. Even in AM stereo, the phase may have shifted, but the carrier frequency remained constant. If you do not understand all the concepts of the AM superheterodyne receiver at this point, it is recommended that you review your You Can Do video on AM radio before proceeding with this video on FM, since many of the circuits will be somewhat similar in operation. This You Can Do video will concentrate on the principles of frequency modulation. You will see that the amplitude of the FM carrier will remain constant while the frequency of the carrier will deviate or change from its center frequency when information is applied to the carrier signal. Then you will progress into the various circuits contained in a typical FM superheterodyne receiver. You will learn about mono and stereo circuits. We will begin by examining the FM signal. When the term FM is used, most people think only of the FM radios in their home or automobile. However, frequency modulation is used in two-way communication, radio control devices, and television. Each of these will be covered in detail in separate videos. This video will concentrate primarily on the FM superheterodyne receiver. In frequency modulation, every effort is made to maintain a constant amplitude of the carrier wave. The circuits contained in the FM receiver are not designed to act upon variations in the amplitude of the RF signal. Here you see a representation of an unmodulated FM carrier wave. Notice that the carrier wave is contained within a specified bandwidth. For simplicity, we have limited our cycles of carrier frequency for the specified bandwidth to 10. This unmodulated carrier is referred to as the resting or center frequency of the FM wave. When information is applied to the carrier wave, it will either increase or decrease the number of cycles contained within the bandwidth of the signal. For example, if a loud signal were transmitted on the FM carrier wave, the result would be more cycles being produced within the specified bandwidth. This increased frequency would be demodulated by the FM receiver to reproduce a duplication of the original information being transmitted. Thus, a loud signal would be heard at the receiver. Now suppose the signal is not as loud. When the softer signal is transmitted on the carrier wave, the result becomes fewer cycles being contained within the specified bandwidth. The FM receiver would then detect the reduced frequency of the carrier wave and reproduce a duplication of the transmitted information at the receiver's output. Thus, a soft signal would be heard at the receiver. As you can see, by varying the loudness of the transmitted information, we can cause the resting or center frequency of the carrier wave to change or deviate from its unmodulated characteristics. The frequency will either increase or decrease depending upon the information transmitted. The amount of frequency variation above or below the carrier frequency is referred to as the deviation of the signal. Remember, loud signals cause an increase in the carrier wave frequency, while softer signals cause a decrease in the carrier wave frequency. In an effort to prevent stations operating near the same frequency from interfering with each other, the Federal Communications Commission, or FCC as it is more commonly called, placed restrictions on the amount in which the center frequency may deviate. The Commission determined that the maximum frequency variance for the modulated FM carrier wave for any FM broadcast station would have a limit of 75 kHz above or below the resting frequency. This allowed the frequency to be varied or deviated a total of 150 kilohertz. However, the process used to modulate the FM carrier will produce many sidebands. Some of these sidebands will be generated beyond the allotted 75 kilohertz initially set by the FCC. Therefore, the FCC permits the transmission of sidebands which fall within 120 kilohertz of the resting frequency. This in effect makes the FM transmission bandwidth a total of 240 kilohertz wide. Sidebands extending beyond the 120 kilohertz deviation must be attenuated by 25 decibels. The band set aside for FM broadcast stations is located in the VHF range of frequencies. It is placed in between television channels 6 and 7. This band extends from 88 MHz to 108 MHz. This band of frequencies is further divided into channels which are 200 kHz wide. Since the permitted bandwidth, including their sidebands, is 240 kHz wide, the FCC will not allow FM broadcast stations in the same area to be assigned adjacent channels. This in effect reduces the channel interference in between adjacent stations. Before continuing into the FM receiver circuitry, we will first examine how the audio information influences the modulation process of the FM carrier wave. As you can see, when the audio information is applied, the frequency of the carrier wave will either increase or decrease. When the audio signal crosses the center line, which corresponds to zero audio voltage, the resting frequency will be transmitted. You may have noticed the frequency of the carrier wave increased with the positive peaks of the audio signal and decreased with the negative peaks. In reality, the FM transmitter can be designed to operate in the manner which is being shown to you now, or in such a way that the frequency decreases at the positive peaks and increases at the negative peaks. The important point to remember is that the amplitude of the audio signal controls the amount of frequency deviation contained in the FM carrier wave. The process used to produce the frequency modulated carrier wave at the transmitter is somewhat complex in nature and therefore will not be covered in detail in this video. At this time, we will pause for a short review of the material just discussed. After the review, we will begin our examination of the FM receiver. The signal being transmitted by an FM broadcast station will vary in frequency while the amplitude remains constant. The unmodulated FM carrier wave is said to be at its center or resting frequency. Depending upon the audio information being applied, the resting frequency will either increase or decrease in frequency. The bandwidth, including all sidebands, should not exceed 240 kHz. This allows 120 kHz deviation above and below the center frequency. All sidebands extending beyond the 240 kHz band must be attenuated by 25 decibels. The total bandwidth for the FM broadcast ranges from 88 to 108 MHz. This band is further subdivided into channels which are 200 kHz wide. The FM broadcast station is permitted to use the entire 200 kHz channel to which it is assigned. Deviation is a term used to describe a change in frequency of the unmodulated FM carrier frequency. The signal may deviate above or below the unmodulated resting frequency. This concludes review number 1. Here you see a block diagram of a typical FM superheterodyne receiver. Through your study of AM radio, you should already be familiar with many of the circuits associated with this FM system. At this time, we will briefly discuss the overall function of the various blocks contained in this FM receiver. We will begin with the RF amplifier. The incoming signal is first applied to the RF amplifier stage. The RF stage might contain a bipolar junction transistor configured in a common emitter or common base circuit, or it might contain a field effect transistor as the amplifying device. The primary function of the RF stage is to amplify the weak incoming signal, then feed this amplified signal into the mixer stage. As you can see, the mixer stage is fed by both the RF amplifier and the local oscillator. The local oscillator will generate a continuous waveform which is either 10.7 MHz higher or lower in frequency than the frequency of the incoming signal being fed from the RF stage. For example, if the RF stage was feeding a 100 MHz signal into the mixer circuit, and the oscillator stage was set to operate 10.7 MHz higher in frequency, then the local oscillator stage would produce a 110 MHz signal to be fed to the mixer circuit. At this point, the mixer stage will heterodyne the two signals and produce the sum and difference of the frequencies which contain the modulated information. This new intermediate frequency is then fed into the first IF amplifier stage. The IF amplifier stage will use the difference frequency between the RF signal and the local oscillator signal. Most FM receivers will have a minimum of 2 IF amplifier stages and may contain as many as 4 such amplifiers. The IF amplifier stages actually provide most of the amplification of the incoming signal. Next, the signal is fed into the FM limiter stage. Not all FM receivers will contain this stage. The primary function of the stage is to clip and smooth out any amplitude variations which may exist in the FM signal. The signal is then fed into the FM detector section. The detector stage is used to remove the audio information from the FM carrier. Since this detector responds to variations in frequency and not amplitude, its operation will be quite different from the detector circuit studied previously in the AM receiver. Next, the signal is fed into a 19 kHz amplifier. This stage also amplifies the L plus R and L minus R signals. The 19 kHz amplifier contains two outputs, one of which goes to a frequency doubler circuit, which increases the frequency to 38 kHz. This new frequency is then fed into a 38 kHz amplifier, where it is amplified and passed into the multiplex demodulator stage. The second output of the 19 kHz amplifier goes directly to the multiplex demodulator section. The multiplex demodulator stage then detects and separates the left and right audio channels from the complex signal. The left and right audio signals are then fed into identical audio circuits. The audio frequency amplifiers boost the signal strength to a level sufficient to drive the power amplifier sections. The power amplifiers are typically designed in a push-pull configuration so that enough power can be generated to operate the speakers. Before proceeding into the individual circuits used in the FM receiver, we will pause for a short review. The FM superheterodyne receiver contains many of the same functional blocks as found in the AM receiver. Even though the RF, mixer oscillator, and IF stages are found in both receiver systems, their operating frequencies will be quite different. The audio frequency and power amplifiers, on the other hand, will be almost identical in operation. The local oscillator in the FM receiver will generate a continuous waveform which can be 10.7 MHz higher or lower than the incoming RF signal. Most FM receivers will contain 2 to 4 intermediate frequency amplifier stages. These IF stages provide the majority of the amplification required for the operation of the following sections. The limiter stage is used to clip and smooth out any variations in the amplitude of the incoming frequency modulated signal. The limiter stage may not be present in all FM receivers. The 19 kHz amplifier, frequency doubler, 38 kHz amplifier, and the multiplex demodulator stages are required to produce the effects of stereo. These circuits are used to separate the left and right audio channels. This concludes review number 2. Here you see the schematic of a typical RF amplifier circuit utilizing a PNP transistor as the amplifying device. Capacitor C1, C5, and a capacitor in the tuned circuit of the local oscillator stage are gain tuned so that when the desired channel is selected, the frequencies at the tuned circuits will be tuned together. Inductor L2 and capacitor C1 and C2 form a parallel resonant tank circuit which can be adjusted in between 88 MHz and 108 MHz. Capacitor C3 is the coupling capacitor for the amplifier stage. You may have noticed the base of the PNP transistor is fed by both the input tune circuit and a control voltage from the automatic gain control circuit. The AGC circuit is designed so the base of the transistor will be negative with respect to the emitter. This is accomplished by making the voltage at the base less positive than the emitter voltage. If a strong signal is received by this stage, the base becomes more positive. This results in a reduced voltage potential between the emitter and base. This in turn reduces the gain of the stage. Capacitor C5, C6, and inductor L3 form the tuned tank circuit at the output of the amplifier stage. Capacitor C7 is the coupling capacitor for the next stage. Due to the high frequencies used in the FM RF amplifier stage, special problems exist in both designing and repairing these units. Even small amounts of lead inductance and stray capacitance will affect the tuning and operation of these very high-frequency amplifiers. The induced fields of electromagnetic energy and stray capacitance could become sufficient to cause the circuit to oscillate. Therefore, great care must be taken when repairs are made. When a component is replaced, its leads must be the exact length as the leads of the faulty component, and the new leads must be set back to the position of the original component. This is so important that many manufacturers often issue instructions on how to dress the leads for the new component. Any components which are replaced must be replaced with the exact specifications used in the original component. Even something as simple as moving a component, like a capacitor, to the side for the purpose of troubleshooting could cause the circuit to oscillate. Next, we will examine a typical FM mixer oscillator stage. Here you see a two-stage mixer oscillator circuit from an FM receiver. Notice that the mixer stage contains two tuned circuits and a junction field effect transistor. You may have also noticed that the tank circuit at the output is contained in a shielded can to eliminate stray voltages which would affect the operation of the circuit. The output being fed into the first IF amplifier stage is 10.7 MHz. The tuned circuit feeding the mixer stage may be adjusted from 88 MHz to 108 MHz. The tuned circuit of the local oscillator stage, which consists of capacitor C12, C13, and inductor L5, are gain tuned with the input of the RF amplifier stage and the input of the mixer stage. You may have also noticed that the frequency of the oscillator can be varied from 77.3 MHz to 97.3 MHz. The local oscillator is generally operated at a lower frequency than the mixer stage to take advantage of the frequency stability at lower operating frequencies. However, the oscillator stage could just as easily operate at a frequency of 10.7 MHz higher than the incoming RF signal. Now let's examine the operation of this circuit. The selected signal from the RF amplifier stage is fed into the parallel resonant tank circuit, which consists of capacitors C8, C9, and inductor L4. The incoming signal then feeds through coupling capacitor C10 and into the gate of the junction field effect transistor. This signal may range from 88 MHz to 108 MHz, the entire FM broadcast bandwidth. As was previously mentioned, the oscillator circuit produces a signal which is 10.7 MHz lower in frequency than the incoming RF signal. This signal is taken from inductor L5 and fed through the capacitor C11 and resistor R4 into the source lead of the JFET device. At this point, the incoming RF signal is fed to the gate, which is heterodyned or mixed with the signal being fed from the local oscillator stage. The mixer stage then produces two additional signal frequencies. One signal is the sum of the two frequencies, and the second signal is the difference between the two frequencies. One important point to remember is that there are actually four separate frequencies present in the mixer stage. You have the selected RF signal, the oscillator signal, the sum of the two, and the difference of the two. Being that the selected signal is frequency modulated, all the signals just mentioned, except the local oscillator signal, will contain frequency deviation when there is modulation present on the incoming RF signal. The sum and difference frequencies are then fed into the tuned parallel resonant tank circuit at the output of the JFET device. The primary of this tank circuit is tuned to 10.7 MHz with a Q factor loose enough to also pass the modulation contained in the deviation of the signal. Therefore, the only signal which will reach the output of the secondary tuned circuit, which consists of L7 and C19, is the difference frequency of 10.7 MHz and its modulated deviation. The other signals contain such a high frequency that capacitors C18 and C17, in effect, act like a short circuit and bypasses these higher signals to ground. The 10.7 MHz deviated signal will not go to ground because the parallel resonant combination of C18 and L6 present a high impedance to the 10.7 MHz signal. Therefore, the IF signal voltage is developed across this combination and may be presented to the next stage of the receiver. You may find a variety of circuit design combinations being used for the mixer oscillator stages. In some receivers, you might find two NPN transistors. In others, you may find two PNP transistors, while in other applications, you could find a single mixer oscillator circuit called the converter stage performing the functions of both the mixer stage and the oscillator stage. It doesn't matter what combination of circuitry is used to perform this function, as long as you understand that the output of the mixer stage will always be a 10.7 MHz center frequency. This has become the standard frequency used for the FM intermediate frequency amplifiers. At this time, we will quickly pause to review the information just presented to you on the RF amplifier and mixer oscillator stages. The RF amplifier stage is utilized to amplify the incoming frequency modulated signal. This stage must be tunable from 88 MHz to 108 MHz, which is the entire FM broadcast bandwidth. The RF stage will generally have an automatic gain control input, or AGC. The AGC is used to control the gain of the stage. Strong signals are reduced in gain, while weak signals are increased with gain. Special problems exist in both the design and repair of the RF amplifier stage. Electrical currents may be induced into other portions of the circuit from stray capacitances or stray electromagnetic fields, which can result in the stage malfunctioning. When a component is replaced, its leads must be the exact length of the leads replaced, and the leads must be placed back in the original component's position. Even when troubleshooting the RF stage, care must be taken not to move the components on the board, or the circuit may go into oscillation. The mixer stage heterodynes the incoming RF signal with the signal produced by the local oscillator stage. The new frequency produced by the mixer stage is called the intermediate frequency, or IF. The local oscillator will generally produce a signal which is 10.7 MHz lower in frequency than the incoming RF signal. However, there are local oscillator stages which operate at a frequency of 10.7 MHz higher than the incoming RF signal. Regardless of the operating frequency range of the local oscillator stage, the output of the mixer stage must always be a center frequency of 10.7 MHz. This is an industry standard. FM receivers, as well as AM receivers, may combine the mixer and oscillator stages into a single stage called the converter stage. This concludes review number 3. Here you see a simplified schematic diagram of a 3-stage intermediate frequency amplifier network. As we have mentioned, the majority of the amplification being received by the incoming signal is produced by the intermediate frequency amplifier stages. The IF stages must not only provide the high gain amplification and selectivity, they must also provide a wide bandwidth. Let's take a quick look at the standard FM IF bandwidth. Here you see a typical response curve for a frequency modulated IF amplifier stage. Notice that the 10.7 MHz resting frequency is located in the middle of the response curve. Since the linear portion of this curve has a typical bandwidth of 240 kHz, the intermediate frequency carrier will be able to deviate 120 kHz above or below the resting frequency point. The response curve of the FM system will normally be tuned so there is a 30 kHz guard band at the high and low frequency ends of the response curve. This, in effect, makes the total IF bandwidth 300 kHz wide. All frequencies falling outside of the 300 kHz bandwidth would naturally be attenuated by 25 decibels or more, and therefore would not be amplified by the IF stage. Now let's return back to the IF amplifier stages. As the signal from the mixer stage enters the primary side of T1, it becomes inductively coupled to the secondary. The secondary of T1 is a parallel resonant tank circuit which is tuned to 10.7 MHz. The circulating current in the parallel resonant tank circuit will continually add to or subtract from the voltage being applied at the base of transistor Q1. This results in transistor Q1 increasing or decreasing its current flow through the primary side of T2 at a rate of 10.7 MHz. Notice that the current flow through Q1 begins at ground, then flows through the emitter of Q1, through the primary side of T2, then from the tap at the lower end of the primary side of T2, then to B+. From here, the signal is inductively coupled to the secondary side of T2. At this point, the signal is taken from the tap at the lower end of the secondary of T2 and fed into the second IF stage. Once again, the circulating current in the parallel resonant tank circuit of T2 causes transistor Q2 to increase or decrease its current flow. The output of Q2 is fed directly into the base of Q3, the transistor of the third IF stage. As the signal being applied at the base of transistor Q3 increases or decreases, it causes the transistor to conduct more or less current. The signal at this point is still 10.7 MHz with a 300 kHz bandwidth. The output of transistor Q3 is fed directly into the primary side of T3, which, as you can see, is a parallel resonant tank circuit. Both the primary and secondary sides of T3 are tuned to the 10.7 MHz center frequency. The signal is then taken from the secondary side of T3 and fed into the next stage, which is usually an FM limiter stage. The FM signal generated at the output of the final IF amplifier stage may contain variations in the amplitude of the FM signal. The function of the limiter stage is to clip both the top and bottom portions of the FM signal to produce a smooth FM wave, free of amplitude variation. It is common to find the limiter stage being described as the fourth IF amplifier stage. This stage will generally be an integrated circuit like the one being shown to you now. Notice that the symbol resembles that of an operational amplifier. In reality, this circuit does use differential amplifiers and will increase the gain of the signal. It is also common to find this type of circuit used to maintain the signal level required for the demodulator stage to function properly. To better illustrate the operation of the limiter stage, we will examine this simple single-stage limiter circuit. Bear in mind, though, the limiter circuit you will generally find in a typical FM receiver will be an integrated circuit, like the one previously shown to you. However, this circuit will give you an understanding of how the stage works. Resistors R1 and R2 are chosen so that the forward bias across the emitter-base junction of the transistor is very low. Since the threshold of the transistor is low, it does not require much of a negative going signal to cause the transistor to go into cutoff. When the transistor is in its cutoff region, its collector voltage will reach its maximum level, even though the signal driving the base will go even further negative. Since the current through the transistor cannot decrease below its cutoff point, the top of the voltage waveform at the output will become clipped. In addition, the value of resistor R3 is chosen so that the collector voltage on the transistor will also be quite low. Therefore, when a small positive going signal is applied to the base of the transistor's collector current will increase to saturation. As the collector current increases, so does the voltage drop across resistor R3. As the voltage drop increases across resistor R3, it decreases the collector emitter voltage of the transistor. The collector voltage at this point drops to almost zero, even though the positive bias at the base of the transistor is still increasing. This results in the bottom of the waveform being clipped. As you can see, by clipping both the top and bottom of the FM signal, any amplitude modulation that might have been induced into the signal can be effectively removed. This type of limiter circuit is seldom used due to the fact that it reduces the overall gain of the FM signal. However, its operating principle is utilized in the more complex limiter circuits. As was mentioned earlier, the majority of limiter stages will use an integrated circuit. This is due to the fact that they are fairly inexpensive, produce very high gain, provide excellent limiting, and are very reliable. At this point, we will stop for another short review of the material just discussed. The intermediate frequency amplifier stage is tuned to a frequency of 10.7 MHz. These stages must allow the resting frequency to deviate a total of plus or minus 120 kHz. The bandwidth of the IF stages is set at 300 kHz. This allows 240 kHz of signal deviation to be amplified equally. There is also a 30 kHz guard band on each end of the 240 kHz signal bandwidth. These guard bands are used to prevent one broadcast station from bleeding into another station's frequency range. The FM limiter stage is used to eliminate any amplitude modulation which may exist in the FM signal. This is accomplished by forcing the limiter stage into saturation, or into cutoff. This concludes review number 4. The simplest form of FM detector is the slope detector, being shown to you now. The slope detector is not used for FM broadcast reception because the fidelity obtained from this circuit is not particularly good. The slope detector is generally used in narrowband FM reception, where the deviation is only plus or minus 5 kHz. The slope detector derives its name from the fact that the resting frequency is on the slope of the response curve of the final IF stage. Basically, the IF transformer in the final stage is detuned to a resonant frequency, which places the resting frequency at about midpoint on the response curve. As you can see in the response curve shown, the final IF transformer is tuned to a resonant frequency of 90 kHz. Now let's see what happens when the RF input is frequency modulated. When the primary side of T1 becomes positive at the top with respect to the bottom of T1, the current will flow from the bottom to the top of the primary side of T1. This causes the current in the secondary of T1 to flow from the bottom of the coil to the top of the coil. The current then flows into the junction of C3 and R1. From here, the current flows through the diode and back to the bottom of the secondary of T1. Since current is flowing through resistor R1, it will develop a voltage drop with the polarity being shown. Since capacitor C3 is connected in parallel with resistor R1, it will charge to the potential being developed across R1. During the second half of the cycle, when the current reverses, the anode of diode D1 becomes negative, which results in no current flow through the diode. At this point, capacitor C3 will begin to slowly discharge through resistor R1. The values of R1 and C3 are chosen so capacitor C3 discharges very little during the negative half of the cycle. This holds the potential on R1 almost constant. Now, suppose the resting frequency deviates to 95 kHz. As you can see from the characteristic curve, the output voltage being taken across the R1-C3 combination increases in voltage. This is due to the fact that the frequency is higher up on the response curve. Now, the resting frequency has deviated down 10 more kHz to 85 kHz. As you can see from the response curve, the output voltage taken from the R1-C3 combination will vary accordingly, thereby producing an audio output. If the FM deviation were to become greater than the linear slope of the response curve, distortion would be produced. For this reason, only narrowband FM can be detected with this circuit. Here you see the well-known Foster-Seeley FM discriminator circuit. This discriminator circuit converts phase variations, rather than frequency variations, into a positive or negative audio signal. Due to the Foster-Seeley discriminator's sensitivity to amplitude variations, it is always preceded by one or more limiter stages. Basically, the Foster-Seeley circuit demodulates the FM signal by comparing the phase of the output from the limiter stage with the signal being developed across inductor L2. The audio output voltage will be proportional to the difference of the two signals. To understand how the Foster-Seeley circuit operates, it is necessary to examine the voltage relationships between the various voltages and currents in the circuit. The basic operation of the Foster-Seeley discriminator circuit depends on the phase relationship in between voltages E1, E2, and the voltage drop across inductor L3. The voltage developed across L3 is considered the in-phase voltage, while the voltage values of E1 and E2 are the phase-shifted voltages. To better understand how this circuit works, let's follow the signal from the input to its output. We will examine the circuit while it is at resonance, below resonance, and above resonance. As the signal from the limiter stage enters the Foster-Seeley circuit, it divides and takes two different paths. Part of the signal enters the resonant tank circuit, consisting of capacitor C1 and inductor L1. The other part of the signal is fed to the center tap junction of inductor L2 and coil L3. Since the same signal is applied to both L1 and L3, inductor L3 is effectively in phase with the output signal from the limiter stage. This makes the signal across L3 the reference signal. The signal being applied at inductor L1 is electromagnetically coupled to inductor L2. The voltage induced in L2 causes a current to flow through the coil, which is in phase with the induced voltage. However, the induced voltage flowing through the coil also develops a voltage across the coil, which will lead the current by 90 degrees. This places the voltage across inductor L2 90 degrees out of phase with the reference signal. Since inductor L2 is center tapped, we must consider the voltage potentials in between the center tap to the top of the coil and in between the center tap to the bottom of the coil. These potentials are labeled E1 and E2. Now let's suppose for a moment that the top of inductor L2 is positive with respect to the bottom of L2. If we were to measure the potential from the center terminal to the top of the coil, we would obtain a positive reading. And when we measure from the center terminal to the bottom of the coil, we would obtain a negative reading. This is due to the fact that, by using the center terminal as a reference, the opposite ends of the coil are placed 180 degrees out of phase. This can be better illustrated with the use of a vector. Notice the reference line is marked EL3, which is the in-phase line going to inductor L3. Voltage E1 leads the reference line by 90 degrees. In essence, the voltages are 180 degrees out of phase with one another. By obtaining the vector sum, we can calculate the voltage across each half of the circuit. Notice, when the signal is at resonance, the vector sums ES1 and ES2 are of equal length. Since ES1 and ES2 are equal in value, there will be an equal amount of current flowing through both sections of the discriminator circuit. This results in the voltages being developed across resistors R1 and R2 being equal, but of opposite polarity. The net result is the total voltage being developed across the pair of resistors will be zero, since the two values cancel one another. Therefore, the output of the discriminator will be zero. Now let's see what happens when the FM signal deviates above the resonant frequency. As you can see from the vector diagram, when the incoming FM signal deviates above the resonant frequency, the inductive reactance of L2 will become greater than the capacitive reactance of C3. This causes the circuit to act more like a coil, which means the induced voltage and the secondary current are no longer in phase. This results in the secondary current lagging the induced voltage by a proportional amount. By now, you should have noticed the difference in length between vector sums ES1 and ES2. ES1 has the greater length and therefore the greater voltage drop. Since ES1 and ES2 are no longer equal in value, the current flow through the top and bottom parts of the circuit will no longer be equal. Since ES1 has the greatest potential, resistor R1 and diode D1 will conduct the heavier current flow. This results in the voltage drop across resistor R1 being greater than the drop across resistor R2. The net result is, the output of the discriminator circuit will be a positive value. Now let's see what happens when the FM signal deviates below the resonant frequency. When the frequency modulated signal is below the resonant frequency, the inductive reactance of L2 will be less than the capacitive reactance of capacitor C2. This will result in the circuit acting like a capacitor, in which case the secondary current will begin leading the induced voltage. As you can see from the vector diagram, some voltage 2 now has a greater potential than some voltage 1. Once again, ES1 and ES2 are no longer equal in value. Since ES2 has the greatest potential, resistor R2 and diode D2 will pass the majority of the current. This results in the voltage drop across resistor R2 being greater than the voltage drop across resistor R1. This causes the output of the discriminator circuit to produce a negative output. Resistor R3 and capacitor C6 form a de-emphasis circuit which must be used in the FM broadcast receiver. This is because the FM broadcast transmitter will amplify or emphasize the higher audio frequency program signals more than it would the lower audio frequency signals. Therefore, a pre-emphasis circuit with a time constant of 75 microseconds is used at the FM broadcast transmitter. The signal is then de-emphasized at the receiver with a similar 75 microsecond time constant circuit. As you can see, when the FM signal deviates above or below the resonant frequency, a positive or negative voltage will be developed at the output of the Foster-Seeley discriminator circuit. Since the FM signal deviates at the audio rate, an audio signal will be reproduced at the output of this circuit. The amplitude and frequency of the audio signal will depend on the deviation of the broadcasted FM signal. Next, we will examine the most popular FM detector used in today's modern FM receivers. The most widely used FM detector today is the ratio detector, being shown to you now. Its popularity is due to the fact that it is insensitive to variations in the amplitude of the incoming RF signal. This means the ratio detector does not require the use of preceding limiter stages like those commonly found in the older receivers, which used the previously discussed Foster-Seeley discriminator. The front end of the ratio detector works the same way as the discriminator circuit just discussed. Notice the orientation of diodes D1 and D2 in this circuit. They are biased in a series configuration, so they may conduct together on the same half cycle of the IF signal. This is the easiest way of identifying whether the detector is a ratio detector or a discriminator. The arrangement of capacitor C4 and C5 provides a voltage divider, which reflects the changing reactance characteristic of the circuit. The voltage at the junction of capacitor C4 and C5 is then compared with the average voltage level contained in the last portion of this circuit. Now notice the last portion of this circuit containing capacitor C7 and resistors R1 and R2. Capacitor C7 is of such a large value that it discharges very slowly through resistors R1 and R2. In fact, the discharge is so slow that the negative voltage potential at the top of resistor R1 is directly proportional to the average IF signal's input level to this circuit. Therefore, the top of resistor R1 may be used as an automatic gain control output. The RC time constant of this section of a ratio detector is what makes this circuit withstand instantaneous variations in amplitude of the incoming RF signal. This feature enables the ratio detector to be used without a limiter circuit at its input. Resistors R1 and R2 have equal values, and their junction determines a reference for ground. The voltage level between this portion of the circuit and the voltage level at the junction of capacitors C4 and C5 establishes a difference of potential as compared to the reference ground and the audio output. Therefore, the output of this circuit represents a ratio or average of two voltage potentials. The basic operation of the ratio detector is very simple. When the tank circuit of inductor L2 and capacitor C3 is at resonance with the input signal, there is no current lead or lag to upset the balance of the circuit. Therefore, diodes D1 and D2 will both conduct equal amounts of electricity for capacitors C4, C5, and C7. Capacitors C4 and C5 are tied together in a parallel circuit configuration, with the tie point being used as the ratio output between the charges contained in capacitors C4 and C5, and the grounding bias of C7. With the circuit balanced, the equal charges in capacitors C4 and C5, the ratio of voltage will be 0 at the output. Capacitor C7 maintains a steady voltage potential across the top of capacitor C4 to the bottom of capacitor C5, so amplitude variations in signal strength won't affect the overall operating range of the ratioed output. When the IF signal deviates below the resonant frequency of the L2-C3 tank circuit, the balance of the circuit will tilt. Capacitive reactance will overcome the inductive reactance, thus causing the current to lead the voltage. Diode D2 will conduct more than diode D1, sending more current to capacitor C5 for charging than the current being sent to capacitor C4. Capacitor C5 will have more charge than capacitor C4, which will make the ratio output less positive compared to the voltage potential at the top of capacitor C7. Keep in mind that even though the two halves of the circuit are out of balance, capacitor C7 looked at the average power of both halves of the circuit and maintained a reference voltage potential. When the IF signal deviates above the resonant frequency of the L2-C3 tank circuit, the balance of the circuit will tilt the other way. Inductive reactance will overcome the capacitive reactance, which will cause the current to lag the voltage. Diode D1 will pass more current to charge capacitor C4 than the current being applied to capacitor C5. The ratio output thus becomes more positive. Capacitor C7 still maintains its reference voltage potential. At any time the ratio detector is not at resonance or unbalanced, the audio output from this circuit will be the difference of potentials at EX and EY. Because the ratio detector operates on half cycles of the IF frequency and a charge is applied on capacitor C7 with its biasing arrangement, the audio output is limited to a level half that of the Foster-Seeley discriminator. This is the trade-off of output power for amplitude stabilization. The operation of a ratio detector may also be illustrated as follows. The input signal becomes rectified in the ratio detector where its amplitude establishes a DC operating range through which capacitor C7 is charged. A reference voltage is determined by the biasing arrangement applied to capacitor C7. Therefore, the reference voltage is approximately 1/2 of the DC operating range. With the reference voltage being used as the signal ground, any voltage level above this reference will be positive, and any voltage level below the reference will be negative. Since the ratio detector operates on the IF frequency of 10.7 MHz and will experience above and below resonance conditions, a frequency response of 400 kHz on each side of the IF frequency is a typical bandwidth for this detector. As the signal in the detector increases in frequency from below resonance to above resonance, an S-shaped response curve is realized. However, the entire response curve is not used due to each FM channel having an assigned bandwidth of 200 kHz. Now we can put the voltage potentials of EX and EY into perspective, along with the circuit's capacitive and inductive reactance characteristics. We will now briefly pause to review the material just discussed. The slope detector is the simplest of FM detectors. This circuit design is detuned to operate on the side of its response curve. Since there is not much frequency spread on the side of a response curve, the slope detector is limited for use in narrowband FM applications. The center tap secondary tuned tank circuit is used by the Foster-Seeley discriminator and the ratio detector. The center tap enables a reference to be established for determining various voltage levels of each half of the circuit based on the capacitive and inductive reactances at work in the secondary tank circuit. The Foster-Seeley discriminator design requires one or more limiter stages to precede its input. Because any amplitude variations in the input signal will affect the output of the discriminator, the Foster-Seeley discriminator acts upon phase variations within the FM signal instead of the FM signal deviation. The ratio detector is not sensitive to amplitude variation in the input as with the FM discriminator. Notice the end of the ratio detector circuitry. Capacitor C7 and resistors R1 and R2 are used to maintain a reference voltage potential across the circuit, so amplitude variations won't affect the output. The easiest way to tell the difference between a ratio detector and an FM discriminator is by looking at the orientation of the diodes in the detector circuit. The S-shaped response curve easily depicts the operating characteristics of the ratio detector and also helps to explain the relationship between frequency, reactance, and voltage potential with respect to ground reference. This concludes review number 5. Your You Can Do videos will help you prepare for future job opportunities and will enable you to become well respected in your chosen field of electronics. The better you understand the basics, the more competent you will become when working with electronic equipment. We recommend that you view this video often to gain the full benefit of the material presented. After you have successfully completed this portion of FM radio, you should continue your education with the You Can Do FM Radio Part 2 video. Welcome to FM Radio Part 2. This video will continue where FM Radio Part 1 left off. If you have not studied FM Part 1 to your full understanding, it is recommended that you do so before proceeding with this FM Radio Part 2 video. As you recall, FM Radio Part 1 ended at the detector stage. We will now continue with the signals found at the output of the detector stage. All FM stereo detectors at their audio output contain the same information originally placed on the carrier wave by the received FM broadcast station. If the received FM station is broadcasting one channel, or mono, the same audio will be heard coming out of both speakers. The audio frequency spectrum detected will contain the L plus R information, which ranges 50 cycles to 15,000 cycles. If the received FM station is broadcasting stereo, or two-channel multiplex, different and distinct audio will be heard coming out of each left and right speaker. Now, the detected audio spectrum contains two additional parts in addition to the left plus right information. A left minus right supersonic audio signal is centered on the spectrum at 38 kilocycles. This left minus right audio signal lends in separating the left and right audio channels.
The second additional part of the stereo information is a 19 kHz tone or pilot signal. This pilot signal is used as a reference to reconstruct the two independent left and right audio channels. Sometimes an FM broadcast station might also transmit a second program in addition to the main stereo program being broadcast. This secondary program is called Subsidiary Communication Authorization by the FCC. The SCA supersonic signal is usually centered on the spectrum at 67 kHz. The audio information leaves the detector and is passed directly to the 19 kHz amplifier. This amplifier is responsible for not only amplifying the 19 kHz pilot signal, but also separating the pilot signal from the L+R and L-R audio signals. This stage also sharply attenuates the 67 kHz SCA signal, along with the fourth harmonic of the 19 kHz pilot tone being 76 kHz. Let's examine this circuit closer to discover how it functions. All the audio information from the detector stage is capacitively coupled through capacitor C1 and introduced to the base of transistor Q1. Let's examine this circuit closer to discover how it functions. All the audio information from the detector stage is capacitively coupled through capacitor C1 and introduced to the base of transistor Q1. Q1 amplifies everything coming from the detector. The amplified signals are passed from Q1's collector into the LC tank circuit composed of capacitor C3 and inductor L1. The function of the C3 L1 tank circuit is to trap the 19 kHz pilot tone from passing into the lower half of the circuit. Inductor L2 electromagnetically couples with the 19 kHz trap circuit to pick up the pilot signal from the tank circuit. The signal capacitively couples through capacitor C5 and into the base of Q2. Since the pilot tone is much lower in percentage of modulation compared to the L+R and L-R signals, the 19 kHz pilot signal must be increased in amplitude by transistor Q2. The collector of Q2 passes the amplified pilot tone into the C8 L5 resonant tank circuit. This tank circuit is tuned to resonate at 19 kHz and is center tapped on the inductor L5, where the amplified pilot signal may be passed to another stage. The remaining signals are passed through capacitor C3 and into the C4 L3 tank circuit. This tank circuit is tuned to trap out or cancel any 67 kHz SCA signal which may be present in the detected information. The remainder of the signals are passed from capacitor C4 to the L4-C7 tank circuit. Since there is usually a fourth harmonic generated by the 19 kilocycle tone, the 76 kilocycle signal must be removed or noticeable interference will be heard in the audio output of the receiver. This is where the tuned tank circuit, consisting of inductor L4 and capacitor C7, traps or cancels out the 76 kilocycle component. Now the only signals which exist are the L+R and the L-R audio components, which are presented to transistor Q3 for amplification. The amplified L+R and L-R audio signals are taken off the emitter of Q3 and presented to the matrix decoder stage. Since the actual 38 kHz subcarrier was suppressed prior to transmission, only the sidebands exist with the information of the L-R signal. In the receiver, the 38 kHz subcarrier needs to be reinserted for the demodulation of the L-R component to occur in the receiver's matrix decoder section. In order for the 38 kHz subcarrier to exist in the matrix stage, the 19 kHz pilot tone is taken from the 19 kHz amplifier and fed into a frequency doubler. In our example, actually both the frequency doubler and the 38 kHz amplifier are combined into one circuit. Here the 19 kHz pilot tone is doubled in frequency to 38 kHz. Let's take a look at the circuit responsible for doubling the pilot signal. This combined circuit utilizes an emitter-coupled multivibrator technique. Since the emitter-coupled multivibrator was covered in the You Can Do Part 6 oscillator video, we will not go into great detail of its operation. Although circuit design varies, the principles of operation are still the same. However, there are differences which should be pointed out. Notice the 19 kHz input and coupling capacitor C1. This multivibrator circuit is actually able to lock in on the incoming frequency of 19 kHz and produce an in-phase output with the input signal. Also notice that the load resistor on transistor Q2's collector has been replaced with a tuned tank circuit consisting of capacitor C3 and T1's primary coil, which is resonant at 38 kHz. The secondary of T1 provides the double frequency of 38 kHz to the next stage of the receiver. We will now pause for a quick review of the most recently discussed material. The information contained within the frequency spectrum will vary according to whether the FM broadcast station is transmitting only mono or stereo and possibly SCA. The 19 kHz amplifier basically amplifies the L plus R pilot tone, and the L minus R signals, while filtering out any SCA signal and 76 kHz fourth harmonic which may be present. The 19 kHz pilot tone is filtered from one portion of the circuit and passed into another part of the circuit for amplification. The frequency doubler uses the 19 kilocycle tone to produce an in-step 38 kHz second harmonic signal to be used in the following section of the receiver. This concludes review number 1. The matrix demodulator, also called the demultiplex section of an FM receiver, is usually enshrouded in mystery as to the way it separates the left and right audio channels from the composite audio waveform. This portion of the video will remove all mystery of the inner workings of the FM matrix decoder. Let's start off by examining just what is a left plus right and a left minus right audio signal. Both the left and the right channels, or soundtracks, are two identical audio lines with independent signals placed upon them. In order to make a left plus right audio signal, you simply connect or add both left and right audio sources into one output, thus creating an L plus R signal. But what about a left minus right signal? Notice the only difference between an L plus R signal and an L minus R signal is the plus R and the minus R in the expressions. The solution to getting an actual minus R signal involves logic. The minus R signal is produced by taking the normal right audio, or plus R, and running it through a linear inverter, such as an operational amplifier, to get an inverted R, or minus R signal. Now that a minus R signal is readily available for use, we can connect or add both the left audio line with the output of the operational amplifier, which is producing an inverted or negative R audio signal. When both signals are summed together, the result is an L minus R signal. If both L plus R and L minus R processes are combined into one unit, we have an encoder matrix. An encoder matrix is useless without a decoder matrix to reverse the process and separate the original left and right audio signals. Let's quickly go through some of the extreme signal possibilities which could occur in both encoder and decoder matrix designs. Suppose the left soundtrack has audio and the right soundtrack does not. The left audio signal will split in half and travel to the L plus R summing amp, and the other half to the L minus R summing amp. Half to the L minus R summing amp. The output of the L plus R summing amp will be an in-phase reproduction of the left soundtrack, but at half the amplitude, or a half unit. The output of the L minus R summing amp will also be an in-phase reproduction of the left soundtrack, but at half a unit. The decoder matrix uses both halves of L plus R and L minus R signals to reproduce the original information encoded. The half unit of L plus R goes to each left and right audio output. The half unit of L minus R goes to the left audio output and also through an inverter, which makes the entire L minus R signal negative. Notice the waveforms at the left audio output are in phase and reinforce each other, and the waveforms at the right audio output are exactly out of phase and cancel one another. We now have a full unit of left audio and no unit of right audio, which is what we started with at the encoder matrix. Now let's reverse the situation. Suppose there was a right soundtrack and no left soundtrack. Since there is no left soundtrack, there will be no left signal going to either L plus R or L minus R summing amps. However, since there is a right soundtrack, there will be a right signal going to both the L plus R summing amp and the linear inverter. The output of the inverter will be presented to the input of the L minus R summing amp. Notice the outputs of the left plus right and the left minus right summing amps. The L plus R output is in phase with the original right signal, and the L minus R output is 180 degrees out of phase. The L plus R and L minus R audio signals leave the matrix encoder and are sent to the matrix decoder. In the decoder, the L plus R signal goes to both the left and right outputs, while at the same time, the L minus R signal goes to both the left output and through the inverter to the right output. Now notice the waveforms at the left channel and the right channel. The waveforms at the left channel are exactly the same but opposite in phase. Thus they cancel each other out and reproduce no output in the left soundtrack. However, the waveforms at the right soundtrack reinforce each other to reproduce the same right signal as was first seen by both left and right soundtracks of the matrix encoder. Let's look at another possibility where there are two identical waveforms on both left and right soundtracks. The left audio signal, again, goes to both L plus R and L minus R summing amplifiers. The right audio signal goes to the L plus R summing amp and the inverter input, and from the inverter output to the L minus R summing amp. Notice the waveforms at the input of the L plus R summing amp. Both waveforms are exact in amplitude and in phase, so therefore they will reinforce each other to produce a full unit of L plus R output. On the other hand, the waveforms at the input of the L minus R summing amp are exactly alike, but one is opposite in phase to the other. These two waveforms will cancel each other out and will produce no L minus R output, and therefore no L minus R signal will be sent to the matrix decoder's L minus R input. The L plus R signal will be sent to the decoder for processing. The L plus R signal enters the decoder and splits off to the left and right outputs. Since there is no other L minus R waveforms at this instant, nothing will be canceled or reinforced. Therefore, both left and right canceled or reinforced. Therefore, both left and right soundtracks will contain half units of the same signal as was seen by the inputs of the encoder. There is another possibility which could occur. Suppose both left and right soundtracks are carrying exactly the same signal, but one soundtrack, say the right channel,
is out of phase from the left channel by 180 degrees. The left signal, as normal, goes into both the L plus R and the L minus R summing amps, and the out-of-phase right signal goes to both the L plus R summing amp and the inverter input, and from the inverter output to the L minus R summing amp. At this point, the two out-of-phase signals cancel each other out, and no L plus R output emerges from the summing amp. The signals present at the L minus R summing amp will reinforce each other and produce a left minus right output. The L minus R signal travels from the encoder to the decoder. Here the signal splits in half. One half unit of the signal goes to the left channel, while the other half unit goes through the linear inverter and is presented to the right channel. Both the left and right channels of the decoder output reproduce half units of the original signals found at the left and right inputs of the encoder matrix. In this example, the encoder matrix has no L plus R signal to be transmitted to the decoder due to the two out-of-phase signals at the encoder's input. As a rule, it's customary and required by the Federal Communications Commission for both the left and right audio channels to be combined as the main L plus R channel, so a mono receiver is capable of reproducing both left and right audio channels, although not separated from each other. This applies not only to FM stereo, but AM stereo as well. Let's now pause for a review of the material just discussed. An L plus R signal is the combination of both left and right channels, or soundtracks. A minus R signal is generated by utilizing the actual R signal and changing the phase 180 degrees. Although quite a few techniques may be used to reverse the R signal's phase, the linear operational amplifier is the most practical and cost-effective method of signal inversion. The L minus R signal is simply a combination of the L signal with the inverted R signal. A matrix section, whether encoder or decoder, relies upon amplitude and phase variations of at least two different signals to extrapolate the desired waveform. We learned about the extreme waveform conditions which could occur at the encoder and decoder matrices. In actual operation of either matrix, phase relationships should fall in between these extreme broadcast characteristics, reproducing the left and right soundtracks from the original transmitted information. When the left and right input signals of the encoder are exactly out of phase with one another, the result is no L plus R signal to be transmitted as the main channel. This poses no real problem for stereo receivers, but does create a big problem for mono or single channel receivers, since mono receivers use only the L plus R main channel of any broadcasted program. Without the L plus R signal being present in the mono receiver, silence would be reproduced by the single channel radio. This applies to both AM stereo and FM stereo broadcasts. This concludes review number 2. The matrix demodulator stage may use either a frequency division or a time division method of decoding two or more channels of information. Digital multiplex uses time division, while the FM stereo process uses frequency division. One of the circuits which utilizes frequency division is the biplex detector. Here you see a simple biplex detector circuit used in many matrix demodulator stages. Transistor Q1 is a special PNP transistor in which its collector and emitter are interchangeable. This is due to the fact that both p-n junctions are doped equally. Q1 can be better illustrated by looking at this type of transistor as two matched diodes with their cathodes tied together and used as the base connection. Notice this circuit resembles two AM detector circuits put together, or actually a double sideband AM detector. The L-R signal coming out of the detector stage is a double sideband AM signal, but without the 38 kHz subcarrier. When only an L+R signal is applied to the audio input, the diode combination, or Q1, will conduct along with the rest of the circuit and pass the L+R signal to the left and right channels. In order for stereo separation of the left and right signals to occur, the left and right audio waveforms must be isolated. This is accomplished by reinserting the 38 kHz subcarrier into the circuit. Notice the 38 kHz signal gets filtered out from the actual left and right audio outputs by the R3C2 and R6C3 combinations. Now keep in mind, the L+R signal will pass through the circuit without interference from the 38 kHz signal, since both signals are of different frequency components. Remember, this entire circuit is designed around reinserting the 38 kHz subcarrier with the L-R signal and using the L-R information from both sidebands, just as a simple one-diode AM radio detects information from a single sideband. The extracted L-R information is now at the same audio frequencies as the L+R information, and the actual left and right audio channels may now be isolated into their independent soundtracks. The isolation of independent left and right soundtracks is a function of amplitude and phase between the left plus right and the left minus right audio waveforms. As the 38 kHz subcarrier oscillates through the circuit, the L+R and L-R signals will either cancel or reinforce each other to varying degrees. Thus, channel separation is achieved. Another type of circuit used in FM stereo receivers is the multiplex switching unit being shown to you now. Notice there are 4 actual diodes used in this circuit to detect the left and right soundtracks. When there is no L+R or L-R signal present at the input of the matrix stage, the 38 kHz signal will oscillate through the circuit. On the first half cycle of the 38 kHz signal, where the top of the secondary of T1 is positive and the bottom portion of the coil is negative, current will flow from the bottom portion of the coil to the C2R3 junction, through resistor R3, thus charging capacitor C2, and through diode D3 and diode D4, back into the top of the secondary of T1. Notice, capacitor C5 charged when both diodes D3 and D4 were conducting current. During the second half cycle of the 38 kHz signal, the top of the secondary of T1 will become negative and the bottom positive. Current will flow from the top portion of the coil into the C3R4 junction through diodes D2 and D1 and back to the bottom of the secondary of T1. Capacitor C4 charged when diodes D1 and D2 conducted current. Notice, the junction of capacitors C4 and C5 is tied to ground. The left and right audio channels see no signal level since both capacitors C4 and C5 have the same applied voltage but are of opposite polarity with respect to ground. At the L+R and L-R input terminal of the matrix circuit, there are 2 different waveforms applied simultaneously. The first waveform is a normal L+R audio signal. The other L-R signal at this point is still in its AM double sideband form and requires detection. Actually, Both the L plus R audio signal and the L minus R sidebands are intermixed and depict a somewhat complex waveform. During the first half cycle of the 38 kHz signal, when a positive crest of a complex or integrated audio waveform appears at the junction of resistors R1 and R2, diodes D3 and D4 will pass current differently. Diode D3 will conduct less and D4 more, which will in turn charge capacitor C5 positive. If the audio signal contained a negative crest during the same 38 kHz half cycle, then diode D3 would conduct more and diode D4 would conduct less, placing a negative charge on capacitor C5. Charge on capacitor C5. On the second half cycle of the 38 kHz signal, the audio signal at the R1-R2 junction may still be a negative crest. In this situation, diode D1 will conduct less and diode D2 will conduct more, placing a negative charge on capacitor C4. During the same 38 kHz second half cycle, when the audio signal happens to be a positive crest, diode D1 will conduct more than diode D2, placing a positive charge on capacitor C4. Since the 38 kHz signal oscillates through the matrix circuit, and with the varying composite audio signal randomly increasing and decreasing the conduction of diodes, separation of the left and right channels is provided by the charges contained in capacitors C4 and C5. The R5-C6 and C7-R6 resistor capacitor combinations form the de-emphasis network for each half of the left and right circuit. We will now pause to review the material just discussed. Both the biplex detector and the matrix demodulator can be thought of as a double sideband AM detector. The main purpose of these circuits is to reinsert the 38 kHz subcarrier in between the two L-R sidebands, so demodulation of the L-R audio signal results in each half of the circuit. The L plus R and L-R audio signals will react with each other to either reinforce or cancel the other to varying degrees, based upon each signal's amplitude and phase relationship. The 38 kHz subcarrier also directs which half of the circuit the L plus R and L-R audio signals will react, thus providing left and right stereo channel separation. This concludes review number 3. The last portions of the FM superheterodyne receiver are the audio frequency amplifier stages. As mentioned in FM Part 1, these audio amplifier stages are identical in each left and right channel. The first audio frequency stage of this FM receiver is capacitively coupled to its respective output channel from the matrix decoder or biplex detector. Each first stage is composed of two transistors, Q1 and Q2. These NPN and PNP transistors are direct coupled to one another and are biased in the Class A operation mode. The output of Q2's collector is fed into the top of resistor R6, which is used as a voltage divider and performs the function of volume control for its respective audio channel. The second audio frequency amplifier in both left and right channels is capacitively coupled to the output of the first audio frequency amplifier. The audio signal from the previous stage is applied to the base of transistor Q3, which is biased in a Class A operating mode, and as you can see, is an NPN bipolar device. The collector of Q3 not only supplies the current to T1's primary coil, but also supplies current to resistor R7 and capacitor C5, which form the tone control circuit of their respective audio channels.
The power output of these second audio stages is at least 1/2 watt and is inductively coupled through audio transformer T1 to the power amplifier stage. The power amplifier in each left and right channel is a push-pull NPN transistor configuration, biased to operate in either Class AB or B mode. Transistors Q4 and Q5 will supply about 10 watts when large enough heat sinks are used with these transistors. Otherwise, without the heat sinks, about 1 watt of power will be supplied to the output. Both transistors Q4 and Q5 are subject to thermal runaway. As Q4 and Q5 warm up, their conductivity increases, which causes both transistors to conduct more current, thus producing greater heat. Resistor R10, a negative temperature coefficient resistor, is used to regulate the current flow supplied to the bases of Q4 and Q5 through the center tap of T1's secondary winding. R10 will be physically mounted on both transistors Q4 and Q5 to ensure proper heat sampling. As resistor R10 is heated by both transistors, its resistance lowers, thus reducing the flow of current to transistors Q4 and Q5, preventing thermal runaway. Audio transformer T2 is used to efficiently transfer power from this stage to either speakers or a separate, more powerful amplifier. In doing so, T2 effectively matches the impedance of this amplifier circuit to the impedance of the load. We will briefly pause for a review of the material just discussed. Resistor R6, a potentiometer, provides the volume control for its respective audio channel. The second audio frequency stage performs in a Class A operating mode. Potentiometer R7 and capacitor C5 form the tone control for its respective audio channel. The power developed in this stage will be at least 1/2 watt and inductively coupled to the power amplifier stage. The power amplifier stage operates in either a Class AB or Class B mode and uses a push-pull transistor configuration. A negative temperature coefficient resistor is mounted to both NPN power transistors to prevent thermal runaway of the stage. The output transformer properly matches stage impedance to the load impedance. As you will see, when the first audio frequency amplifier, the second audio frequency amplifier, and the power amplifier are joined together, the result is an audio frequency amplifier section capable of boosting the input signal to a considerable amplitude. This concludes review number 4. In the beginning of this video, we mentioned that an FM broadcast station might also transmit a second program in addition to the main broadcast. This second program is called Subsidiary Communication Authorization, or SCA. The SCA signal is basically used for background music, station-to-station communication, and telemetry, such as studio transmitter links, or STLs. Most SCA signals are not intended for use by the general public, and a subscription fee may be required for legal reception of the SCA service. If in doubt, contact the FM station which is broadcasting the SCA signal to determine proper usage of their SCA transmission. The SCA signal, before being placed on the main FM carrier, is a double sideband suppressed carrier similar to the L-R information, but with lower modulation power in its sidebands and containing a narrow bandwidth of only 15 kHz. Because of the 15 kHz bandwidth, Each sideband will extend plus or minus 7.5 kHz from its suppressed carrier. Unlike the L-R information, the SCA signal does not use pre-emphasis at the transmitter and therefore does not require de-emphasis when used at the receiver. The SCA information may be located anywhere between 20 and 75 kHz on the audio frequency spectrum or baseband of the main FM carrier with respect to bandwidth already in use. If the FM station is broadcasting stereo multiplex, the SCA signal will be placed after the multiplex information, usually at 53 to 75 kHz, with the suppressed carrier having a frequency of 67 kHz. Sometimes a second SCA signal is centered at 92 kHz in areas where FM stations are far enough apart on the FM band not to cause interference with surrounding radio equipment. If the FM station is broadcasting mono, then there will be no stereo multiplex information requiring bandwidth space, and consequently, the SCA portion of the transmission may be moved down to a lower position within the baseband of the FM carrier. The basic FM receiver is unsuitable for SCA reception because it filters out the SCA component, and the audio portion is put through de-emphasis prior to audio amplification. To properly demodulate the information of the SCA signal, its suppressed carrier frequency must be known, and a special SCA decoder must be used. The SCA decoder should be tied in just after the main detector stage, but before the 67 kHz SCA trap. In our example, the SCA detector will receive its input from the output of the main detector stage, just as the 19 kHz amplifier stage does. The detected SCA signal can be switched into the audio frequency stages for amplification. We will now pause for a review of the material just discussed. The SCA signal is a double sideband suppressed carrier which is placed on the FM baseband, usually around 67 kHz. SCA transmissions are usually not intended for use by the general public. Any unauthorized use of an SCA service may be deemed illegal. This concludes review number 5. RBDS, or Radio Broadcast Data System, is centered around a method of transmitting digital information via an FM broadcast station to receivers in the listening area. RBDS and RDS, or Radio Data System, are two basically compatible systems, although RDS first originated in Europe and has been used for quite some time. RBDS is the standard adopted by the United States and the system we will examine. Since RBDS and RDS are so similar in design and operation, the two systems may be thought of as one for the remainder of this video. RBDS and RDS, like other SCA signals, use a double sideband suppressed carrier placed on the FM baseband, where it is centered at 57 kHz. The RBDS signal has a maximum bandwidth of plus minus 2.4 kHz. During an RBDS transmission, the 57 kHz subcarrier is generated independently by the RBDS encoder. An FM station which is also broadcasting stereo multiplex will provide a 19 kHz pilot signal to the RBDS encoder, which uses this pilot signal as a reference to phase lock the 57 kHz subcarrier to the pilot signal. The RBDS binary data is converted into a biphase signal which amplitude modulates the sidebands of the 57 kHz subcarrier. The biphase method of data transmission offers the receiver no direct way of determining which phase is a logical one
or a logical 0. However, this drawback has been overcome by differentially encoding and decoding the data. The various data formats which are incorporated in RBDS are beyond the scope of our discussion and will not be covered in this video. However, we will start off by examining the basic data structure of RBDS. Each RBDS data group is composed of 104 bits of binary data and is subdivided into 4 blocks per group. Each block consists of 26 bits and is further broken down into an information word, which is 16 bits in length, and a check word, 10 bits in length. The 16-bit information word is comprised of any needed or required data. The check word basically provides synchronization necessary for the receiver to implement error correcting when data dropout or data slippage occurs. Since we now understand the fundamentals of RBDS, let's apply this knowledge in discovering how the RBDS encoder operates. The clocking for the RBDS encoder, as mentioned previously, is generated by a 57 kHz oscillator, which is phase-locked to the 19 kHz pilot frequency when stereo multiplex is used by the FM broadcast station. The 57 kHz clock signal is divided by 24, so a clock rate of 2.375 kHz is provided to a delay stage of the encoder. The 2.375 kHz clock frequency is further divided by 2, where 75 kHz clock frequency is further divided by 2, where a clock rate of 1187.5 bits per second establishes the baud rate for serial data transmission into the RBDS encoder. This baud rate plays an important role throughout most of the encoder process. The RBDS encoder consists of 2 major sections, a differential encoder and a biphase symbol generator. The differential encoder uses an exclusive OR gate and a D-type flip-flop. As you should recall from UCANDO's digital series, the D-type flip-flop delays outputting its input by 1 clock pulse, and the truth table of the clock pulse. And the truth table of the exclusive OR gate is shown here. For every logic operation of the exclusive OR gate, the encoded result gets delayed 1 clock cycle through the use of the D-type flip-flop and then applied to both the next logic operation of the exclusive OR gate and to the biphase symbol generator. It's this process which enables the RBDS receiver to correctly process the incoming data, whether or not the signal phase is normal, as transmitted, or inverted. The overall function of the biphase symbol generator makes use of the differentially encoded data and processes it into a biphase waveform, which is later injected into the station's FM baseband for transmission. The NRZ to polar impulse converter changes the incoming binary format of digital pulse information to positive or negative impulse data. A binary 1 will produce a positive impulse, and a binary 0 will produce a negative impulse. These impulses go to the next section of the biphase symbol generator, where the biphase encoding actually begins. The NRZ to polar impulse converter releases a positive or a negative going electrical impulse. This impulse travels directly to both the delay and the positive input of the amplifier. The amplifier will immediately reproduce an amplified impulse of the same polarity, while the delay holds its impulse. The delay uses the 2.375 kHz clock frequency to offset the release of the delayed impulse. This impulse release will occur in between baud rate cycles of the incoming data. After the impulse travels from the delay to the negative input of the amplifier immediately reproduces an amplified but inverted impulse at its output. As you can see from the chart shown here, the binary representation of positive and negative impulses reflects the actual bi-symbol process of encoding each bit of data. The two impulses representing each bit are referred to as an odd impulse pair. Now, the series of positive and negative going impulses are applied to a shaping filter, where they will basically configure a biphase waveform. The biphase waveform is mixed with the 57 kHz subcarrier to form an amplitude modulated signal, and then the 57 kHz subcarrier is suppressed. The amplitude modulated RBDS information is now injected into the FM baseband along with other program materials, where it is transmitted to the general public. We will now pause for a short review of the RBDS encoder before learning about the RBDS decoding process. The differential encoder processes the incoming data in such a way that either a normal or inverted phase relationship is used when decoding the RBDS data at the receiver. The biphase symbol generator converts the binary encoded data from the differential encoder to data equivalent positive or negative impulses. Each positive or negative impulse lends in generating an odd impulse pair, which is used to form the basis of a biphase waveform through the means of a shaping filter. The biphase waveform modulates the 57 kHz subcarrier, then the subcarrier is suppressed prior to the RBDS amplitude modulation being placed on the FM baseband. This concludes review number 6. The transmitted RBDS information now arrives at the receiver. Receivers equipped to process RDS or RDBS information will contain a special decoder section. The first process of the RBDS decoder is to isolate the RBDS information contained on the FM audio spectrum or baseband from the other program material. An RBDS bandpass filter allows the RBDS portion of the baseband to proceed unchanged into the next stage of the RBDS decoder, while sharply attenuating or rejecting all other baseband frequencies. Now, the filtered RBDS signal splits and is applied to two other stages of the decoder, a 57 kHz amplifier stage and a synchronous 57 kHz demodulator stage. The 57 kHz amplifier stage locks onto the suppressed subcarrier, where it is isolated and amplified prior to being passed to the next sections of the RBDS decoder. The synchronous 57 kHz demodulator stage acquires the raw RBDS information from the bandpass filter. At the same time, the amplified 57 kHz subcarrier is being supplied. The demodulator stage uses the amplified 57 kHz subcarrier to demodulate or separate the 57 kHz component from the 2.4 kHz RBDS biphase signal. Now, only the actual RBDS waveform information remains. A shaping filter, identical in function to the shaping filter contained in the previously mentioned encoder, is also used in the decoder. Ideally, both shaping filters share each half of the overall data channel spectrum shaping. This is done to improve signal-to-noise characteristics. You may have noticed that the 57 kHz amplifier stage also passes the amplified signal into a bit rate clock recovery stage. This clock recovery stage also uses the signal from the shaping filter, which lends in maintaining a reference phase lock of the recovered clock signal. Basically, the bit rate clock recovery stage divides the incoming 57 kHz frequency by 48 to establish a bit rate clocking frequency of 1187.5 bits per second.
This baud rate will provide a timing base for the data decoding and transfer throughout the RBDS decoder system. The actual RBDS data decoding process begins in the decoder's biphase symbol decoder. Notice, in the lower left of this decoder, there is a single-pole double-throw switch. This high-speed switch will toggle according to the clock pulses provided by the bitrate clock in selecting one of the two input sources. The first input source, input A, selects the output of a linear inverter, which instantly reproduces an inverted waveform based upon the output of the shaping filter. This input position is chosen when a logic 0 or low appears on the bitrate clock line. Input B takes the waveform directly from the shaping filter without change. Input B is chosen when a logic 1 or high appears on the bitrate clock line. As the single-pole double-throw switch receives the toggling pulses from the bitrate clock line, the low pulse interval will select input A, which will pass the inverted version of the filtered RBDS waveform through the switch for the duration of the logic state on the clock line. This process effectively decodes the waveform shaped by the odd impulse pair generated with the RBDS encoding technique previously described. Now the waveform is applied to an integrate and dump function. The integrate portion of the function is provided by the amplifier. Portion of the function is provided by the amplifier and the capacitor bridge across the input and output of the amplifier. The dump occurs when a high logic condition on the clock line toggles the switch above the capacitor to a closed position, which discharges or dumps the capacitor's charge. This dumping resets the integrator prior to every summing operation. The integrate and dump process is the decoding equivalent to the logic conditions found at the output of the RBDS encoder's NRZ to polar impulse converter. The next function of the biphase symbol decoder is the slicer. The slicer basically references its input signal to a predetermined voltage threshold. If the input signal voltage is below the established threshold, the slicer will produce a logical 0. On the other hand, if the input signal voltage is above the threshold, the slicer will produce a logical 1. The binary logic of the slicer is transferred to the next section of the RBDS decoder, which is the differential decoder. The differential decoder consists of two D-type flip-flops and an exclusive OR gate. The first D-type flip-flop acts like a logic buffer to keep the slicer from introducing untimely logic changes to input B of the exclusive OR gate, which would result in data error at the output C. The second D-type flip-flop, combined with the exclusive OR gate, performs the actual differential decoding. Input B of the exclusive OR gate receives its logic directly from the output of the first D-type flip-flop, while input A is supplied with the logic of the previous clock cycle through the use of the second D-type flip-flop. As you can see, the exclusive OR gate processes every 2 bits along the incoming serial bit stream during each clock cycle.